I'm Kevin Barton, and we'll be discussing IP routing, and specifically we'll be looking at host IP routing logic and router IP routing logic. We'll also take a few minutes and look at packet encapsulation using layer 2 protocol data units, or PDUs, to forward data at the layer 2. So first, let's consider the logic used by the hosts and routers to forward a packet from the source to the destination. We'll be using an example where we're forwarding packet from the source, which is IP address 150.0.1.110, to the destination, which is the server at IP address 7.0.1.5. The host will be making the first decision on how to forward that packet. Once the host makes a decision on how to forward the packet, then every router subsequent in the transmission from the host to the destination will also make a decision on how to forward that packet. So let's look at the host IP routing logic. First, we're going to make a couple assumptions. First, that the host is on Ethernet LAN, whether it's a wired LAN or wireless LAN. Second, that the host goes through this logic for every packet that it transmits. The host tries to make a determination if the destination IP address is in the same subnet as the host or not. If it's in the same subnet as the host, then it delivers the packet directly to the host at layer 2. If the destination is in a different subnet from the host forwards the packet to the default gateway. This will also be done in layer 2 because the default gateway has to be in the same subnet. It would not go directly to the host. It would go to the default gateway, and the default gateway would route it through however many hops needed to reach the host or the destination network. So let's look at that routing logic in this example. The packet is being sent from source 150.0.1.110 to destination 7.0.1.5. Host will examine the destination IP address and determine if it's within the range of IP addresses that is assigned to the host network. How does the host know what's within the range of IP addresses to its network? It does so by looking at its own IP address and the subnet mask. The subnet mask will tell the host how many host IP addresses are within the subnet that the host is IP address assigned from. And the host can determine not only how many hosts are supported in that network, but also the exact range of IP addresses. So the first IP address within that range and the last IP address within that range. In our example, the subnet mask is a /24, meaning that there is 254 assignable IP addresses within that subnet, and those IP addresses start at 150.0.1.1 and go through 150.0.1.254. The IP address 7.0.1.5 is not within that range of IP addresses, so the host knows that the destination IP address is not within the range of IP addresses or for the sources network. The only decision it has to make with that packet is to send the packet to the default gateway. It knows the default gateway's IP address because it is either statically configured or it is learned through DHCP. The source either already knows the MAC address for the default gateway, or it requests that MAC address using the protocol ARP. Once it has the MAC address for the default gateway, source builds a layer 2 Ethernet frame as it encapsulates the IP packet and forwards it to the router. The router receives the packet and goes through a process of determining how to handle that packet. The first step is to verify that the packet is received without errors. It uses a frame check sequence to verify that the packet is not corrupted. When the source built the Ethernet frame for that IP packet, it computed the frame check sequence and appended the frame check sequence to the frame. The router now takes that same frame and again computes the frame check sequence and compares the results from its computation to the frame check sequence it received with the frame. If they match, then it recognizes that there's no errors with the frame and processes the IP packet. Once it passes the error check, the router strips off the layer 2 header and processes the IP packet. The first step is to look at the destination IP address, compare it to the routing table, and determine if the router has a route to that destination network. If it has a route, it builds another layer 2 header and forwards the frame out the correct interface. So let's look at that in this example. So the router receives the frame from the workstation 150.0.1.110. The router receives the packet, verifies that there's no errors by computing and checking the frame check sequence. Once it verifies there's no errors, it strips off that layer 2 header, then examines the destination IP address. So in this case, the destination IP address is 7.0.1.5 and compares that IP address to the networks in its routing table. In this case, we'll say that the router finds a route to the network 7.0.0.0/9 and knows which interface to send that packet out and forwards that packet out the correct interface. So let's look at that the routing logic in a little bit more detail, because there's a couple other details in there that we didn't cover. First, the router is going to ask itself, do I know a route to the destination? In this case, we said it did know a route to the destination, so it just forwards the packet out the correct frame. But what if the router doesn't know a route to the destination? Before the router discards frame, the router is going to ask, do I have a default route configured, or it could also be referred to as a gateway of last resort configured. So do I have a default route or gateway of last resort configured? If the answer is yes, the router will forward the packet out whatever interface is configured as a default route or gateway of last resort. If the answer is no, then the router discards the packet. So how can we view the routing table within a router? All routers will have some capability to review the IP routing table. The command is similar whether you're using Viata or Cisco. The command show IP route will show the router's routing table. In this case, show IP route shows that the router has one static route and 3 directly connected routes. The static route 0.0.0.0/0 is a mask which represents a default route or gateway of last resort. The first directly connected network 50.50.0.0, 50.50.0.0/16 is the link to our next hop. Network 150.0.1.0/24 is the network that contains the source host. We have one other network that's directly connected, 127.0.0.0/8, and that is just a commonly used loopback network. So again, the router has made a decision that it has a route to network 7.0.0.0/9, and the interface to that network, or the packet should be forwarded out interface 50.50. Forwarded to a router. The next hop router in this case is actually titled next hop router and is forwarded to IP address 50.50.50.2. The default gateway will forward the packet to the next hop router, and the next hop router and every subsequent router between the default gateway and the router with the destination network will make a similar logic decision. So now let's take a look at the decision made by the router that has the network 7.0.0.0/9 directly connected. That router is going to use the same routing logic. It's going to verify the frame check sequence to confirm the packet is not corrupted. Once it passes that frame check sequence, then the router will examine if it has a route to the network 7.0.0.0/9. In this case, it will determine that not only does it have a route, that network is directly connected, and it does not need to forward the packet to another router. So instead, it's going to build an Ethernet frame that includes the MAC address for the host that holds the IP address 7.0.1.5 and forwards the frame directly to that host. So let's look at that encapsulation process in a little bit more detail. In this case, we will be sending a packet from PC1 to PC2. PC1 is going to examine the IP address, the destination IP address for PC2, compare it to the range of IP addresses within its own network, and determine that PC2 is not within its own network. So it makes a decision that that packet goes to router 1, which is the default gateway, and it builds an Ethernet frame by encapsulating a header onto that IP packet. The address for the Ethernet addresses are known as MAC addresses. So the source MAC address is going to be the source MAC address for PC1. The destination MAC address will be for router 1's Ethernet interface FA00. PC1 does not already know the MAC address for router 1's Ethernet interface FA00. It will send an ARP request to learn that MAC address, and once it has the MAC address, then it builds Ethernet frame and forwards the frame to router 1. Router 1 will check verify the frame is not corrupted by checking the frame check sequence. Then it will strip the Ethernet header and examine the destination IP address for the IP packet. It determines that PC2 is directly connected, and it verifies, or it determines by looking at its ARP table if it has a MAC address for PC2, and if it does, then it takes that MAC address and builds an Ethernet frame that encapsulates the IP packet and forwards it directly to PC2. If we were sending it to PC3, then instead it would go to router 2, and router 2 would determine that PC3 is directly connected to router 2 and go through the same process forward back to that. Now, of course, not all networks are Ethernet, and in this case we have Ethernet networks that contain the PCs, but or the link between router 1 and router 2 is a serial link and uses a different protocol between the two routers. Instead of using Ethernet, it uses a point-to-point protocol, but we use a similar process where router 1 will receive a frame from PC1, strip the Ethernet header, determine that the packet needs to go to router 2 over that serial link, and instead of adding an Ethernet header, it would encapsulate with a point-to-point header and forward the frame to router 2. Router 2 then would strip the point-to-point header, examine the packet, determine it needs to go to PC3, which is directly connected, and build Ethernet header and forward it to PC3. And so that's a summary of the routing logic between source and destination.